Packet switching is a digital networking communications method that groups all transmitted data into suitably sized blocks, called packets, which are transmitted via a medium that may be shared by multiple simultaneous communication sessions. Packet switching increases network efficiency, robustness, and enables technological convergence of many applications operating on the same network. Packets are composed of a header and payload. Information in the header is used by networking hardware to direct the packet to its destination, where the payload is extracted and used by application software. Starting in the late 1950s, American computer scientist Paul Barron developed the concept distributed adaptive message block switching with the goal to provide a fault-tolerant. This concept contrasted and contradicted the theretofore established principles of pre-allocation of network bandwidth, largely fortified by the development of telecommunications in the Bell system. The new concept found little resonance among network implementers until the independent work of Donald Davies at the National Physical Laboratory. In the late 1960s, Davies is credited with coining the modern name packet switching and inspiring numerous packet switching networks in Europe in the decade following, including the incorporation of the concept in the early ARPANET in the United States. Concept. One simple definition of packet switching is the routing and transferring of data by means of addressed packets so that a channel is occupied during the transmission of the packet only, and upon completion of the transmission the channel is made available for the transfer of other traffic. Packet switching features delivery of variable bitrate data streams, realized as sequences of packets, over a computer network which allocates transmission resources as needed using statistical multiplexing or dynamic bandwidth allocation techniques. When traversing network nodes, such as switches and routers, packets are buffered and queued, resulting in variable latency and throughput depending on the link capacity and the traffic load on the network. Packet switching contrasts with another principal networking paradigm, circuit switching, a method which pre-allocates dedicated network bandwidth specifically for each communication session, each having a constant bit rate and latency between nodes. In cases of billable services, such as cellular communication services, circuit switching is characterized by a fee per unit of connection time, even when no data is transferred, while packet switching may be characterized by a fee per unit of information transmitted, such as characters, packets, or messages. Packet mode communication may be implemented with or without intermediate forwarding nodes. Packets are normally forwarded by intermediate network nodes asynchronously using first-in, first-out buffering, but may be forwarded according to some scheduling discipline for fair queuing, traffic shaping, or for differentiated or guaranteed quality of service, such as weighted fair queuing or leaky bucket. In case of a shared physical medium, the packets may be delivered according to a multiple access scheme. History. In the late 1950s, the U.S. Air Force established a wide-area network for the semi-automatic ground environment radar defense system. They sought a system that might survive a nuclear attack to enable a response, thus diminishing the attractiveness of the first strike advantage by enemies. Leonard Kleinrock conducted early research in queuing theory which proved important in packet switching, and published a book in the related field of digital message switching in 1961. He also later played a leading role in building and management of the world's first packet switch network, the ARPANET. The concept of switching small blocks of data was first explored independently by Paul Barron at the Rand Corporation in the US and Donald Davies at the National Physical Laboratory in the UK in the early to mid-1960s. About 2000, Barron developed the concept of distributed adaptive message block switching during his research at the Rand Corporation for the U.S. Air Force into survivable communications networks. first presented to the Air Force in the summer of 1961 as Briefing B-265, later published his RAND report P-2626 in 1962, and finally in Report Room 3420 in 1964. Report P-2626 described a general architecture for a large-scale, distributed, survivable communications network. The work focuses on three key ideas. Use of a decentralized network with multiple paths between any 2 points, dividing user messages into message blocks, later called packets, and delivery of these messages by store and forward switching. Barron's work was known to Robert Taylor and J.C.R. Licklider at the Information Processing Technology Office, who advocated wide-area networks, and it influenced Lawrence Roberts to adopt the technology in the development of the ARPANET. Starting in 1965, Donald Davies at the National Physical Laboratory, UK, independently developed the same message routing methodology as developed by Barron. He called it packet switching, a more accessible name than Barron's, and proposed to build a nationwide network in the UK. He gave a talk on the proposal in 1966, after which a person from the Ministry of Defense told him about Barron's work. A member of Davis' team met Lawrence Roberts at the 1967 ACM Symposium on Operating System Principles and suggested it for use in the ARPANET. Davies had chosen some of the same parameters for his original network design as did Barron, such as a packet size of 1024 bits. In 1966, Davies proposed that a network should be built at the laboratory to serve the needs of NPL and prove the feasibility of packet switching. The NPL Data Communications Network entered service in 1970. The first computer network and packet switching network deployed for computer resource sharing was the Octopus network at the Lawrence Livermore National Laboratory that began connecting for control data 6,600 computers to several shared storage devices and to several hundred teletype Model 33 ASR terminals for time-sharing use starting in 1968. In 1973, Vint Cerf and Bob Kahn wrote the specifications for Transmission Control Protocol, an internetworking protocol for sharing resources using packet switching among the nodes. Connectionless and connection-oriented modes. Packet switching may be classified into connectionless packet switching, also known as datagram switching, and connection-oriented packet switching, also known as virtual circuit switching. Examples of connectionless protocols are Ethernet, Internet Protocol, and the User Datagram Protocol. Connection-oriented protocols include X25, Frame Relay, Multi-Protocol Label Switching, and the Transmission Control Protocol. In connectionless mode, each packet includes complete addressing information. The packets are routed individually, sometimes resulting in different paths and out-of-order delivery. Each packet is labeled with a destination address, source address, and port numbers. It may also be labeled with the sequence number of the packet. This precludes the need for a dedicated path to help the packet find its way to its destination, but means that much more information is needed in the packet header, which is therefore larger, and this information needs to be looked up in power-hungry content-addressable memory. Each packet is dispatched and may go via different routes, potentially. The system has to do as much work for every packet as the connection-oriented system has to do in connection setup, but with less information as to the application's requirements. At the destination, the original message data is reassembled in the correct order, based on the packet sequence number. Thus a virtual connection, also known as a virtual circuit or byte stream, is provided to the end user by a transport layer protocol, although intermediate network nodes only provides a connectionless network layer service. Connection-oriented transmission requires a setup phase in each involved node before any packet is transferred to establish the parameters of communication. The packets include a connection identifier rather than address information, and are negotiated between endpoints so that they are delivered in order, and with error checking. Address information is only transferred to each node during the connection setup phase. When the route to the destination is discovered, an entry is added to the switching table in each network node through which the connection passes. The signaling protocols used allow the application to specify its requirements and discover link parameters. Acceptable values for service parameters may be negotiated. Routing a packet requires the node to look up the connection ID in a table. The packet header can be small, as it only needs to contain this code and any information, such as length, timestamp, or sequence number, which is different for different packets. Packet switching in networks. Packet switching is used to optimize the use of the channel capacity available in digital telecommunication networks such as computer networks, to minimize the transmission latency, and to increase robustness of communication. The best-known use of packet switching is the Internet and most local area networks. The Internet is implemented by the Internet Protocol suite using a variety of link layer technologies. For example, Ethernet and frame relay are common. Newer mobile phone technologies also use packet switching. X25 is a notable use of packet switching in that, despite being based on packet switching methods, it provided virtual circuits to the user. These virtual circuits carry variable length packets. In 1978, X25 provided the first international and commercial packet switching network, the International Packet Switched Service. Asynchronous transfer mode also is a virtual circuit technology, which uses fixed-length cell relay connection-oriented packet switching. Datagram packet switching is also called connectionless networking because no connections are established. Technologies such as multi-protocol label switching and the resource reservation protocol create virtual circuits on top of datagram networks. Virtual circuits are especially useful in building robust failover mechanisms and allocating bandwidth for delay-sensitive applications. MPLS and its predecessors, as well as ATM, have been called fast packet technologies. MPLS, indeed, has been called ATM without cells. Modern routers, however, do not require these technologies to be able to forward variable-length packets at multi-gigabit speeds across the network. X25 versus frame relay. Both X25 and frame relay provide connection-oriented operations, but X25 does it at the network layer of the OSI model. Frame relay does it at level 2, the data link layer. Another major difference between X25 and frame relay is that X25 requires a handshake between the communicating parties before any user packets are transmitted. Frame relay does not define any such handshakes. X25 does not define any operations inside the packet network. It only operates at the user network interface. Thus, the network provider is free to use any procedure it wishes inside the network. X25 does specify some limited retransmission procedures at the Uni, and its link layer protocol provides conventional HDLC-type link management procedures. Frame relay is a modified version of ISDN's Layer 2 protocol, LAPD and LAPB. As such, its integrity operations pertain only between nodes on a link, not end-to-end. Any retransmissions must be carried out by higher layer protocols. The X25 Uni Protocol is part of the X25 protocol suite, which consists of the lower 3 layers of the OSI model. It was widely used at the Uni for packet switching networks during the 1980s and early 1990s. To provide a standardized interface into and out of packet networks. Some implementations used X25 within the network as well, but its connection-oriented features made this setup cumbersome and inefficient. Frame relay operates principally at layer 2 of the OSI model. However, its address field can be used at the OSI network layer, with a minimum set of procedures. Thus, it rids itself of many x25 layer 3 encumbrances, but still has the DLCI as an ID beyond a node-to-node layer 2 link protocol. The simplicity of frame relay makes it faster and more efficient than x25. Because frame relay is a data link layer protocol, like x25, it does not define internal network routing operations. For x25, its packet IDs, the virtual circuit and virtual channel numbers have to be correlated to network addresses. The same is true for frame relay's DLCI. How this is done is up to the network provider. Frame relay, by virtue of having no network layer procedures, is connection-oriented at layer 2. By using the HDLC, LAPD, LAPB set asynchronous balanced mode, x25 connections are typically established for each communication session. But it does have a feature allowing a limited amount of traffic to be passed across the Uni without the connection-oriented handshake. For a while, frame relay was used to interconnect LANs across wide area networks. However, x25 and well as frame relay have been supplanted by the Internet Protocol at the network layer, and the asynchronous transfer mode and/or versions of multi-protocol label switching at layer 2. A typical configuration is to run IP over ATM or a version of MPLS.